Greetings, I just checked in a new project and I don't want to get too much into it, but I do think I want to go over the setup process. I think more or less to validate the steps here that I have on my GitHub README. A quick overview, it's a machine learning technology that you can read about up on the ARM website. It's using SVM classifier with the Scikit-Learn basically library, and I'm using the one that comes with ST Electronics for the STM32 controllers and the CM/SYS DSP libraries. And this, I have a model that's trained already, so you don't have to train the model. So I have the header that I generated following the instructions on this website. So for all of that, you should learn that for yourself. But if you just want a demonstration to see how it works, you can use this. But one of the big benefits of this project, besides its applications for using the Scikit-Learn and comparing the results in TensorFlow, is that we're creating a embedded project that has very small binaries compared to what you get when you use like the IDE, the STM32Cube IDE. And also I'm not using the HAL libraries or the standard C libraries, and so the binaries are quite a bit smaller. But at the same time, you can use, you can clone this project and use it with the IDE side by side. It will work. But the binary is much bigger using the IDE, and if you know why, you could comment. I don't understand why it's so big, and maybe using different compilers and stuff. I really don't know. But I do want to go through the setup. So I do have it working on Windows and on Linux, both using the IDE and both using the makefile. But the Windows is a little more complicated. I have the steps here for doing it, but I just want to walk you through the Linux scenario. I think that's the most straightforward. And so very quickly what the program does is it already has a trained Scikit-Learn SVM model. And so it, for data, I trained it with a bunch of live samples right off the board, voltage samples. And so I saved that to a text, using a comport reader. I use UART to have a comport reader, save it, and then train the model with it, and train a TensorFlow model with it. And then also have some known anomaly data that I got from the TensorFlow autoencoder anomaly detection, so I can add false tests to it. So basically I have this using the machine, using the live voltage samples to train, and then I get fresh voltage readings to run as inference against the model. And then I use that same data to test it against TensorFlow. And so it's all working. And by the way, I find the Scikit-Learn for just classification and outlier detection and anomaly detection, I find it a lot more straightforward than NanoEdge. And maybe I just don't really know how to use NanoEdge, but whatever, but that's just my experience. And again, I'm not using HAL. It's just bare metal. I'm not using the library. I'm trying to keep the footprint very small. So there's two modes of running the application. One is to get those samples. So I call that log-only mode. And you have some conditional compilations in the code. And then there is the inference mode, where you already have the trained model and you're on the board, you're running it through. You're taking the live samples and running it through the model and getting your results and reading it on a comport reader. And then for the extra step, if you want, you can save those results and to a file, and then open that file in a script that I have checked in that opens up a Keras model, TensorFlow Keras model, and to see if you're getting comparable results, both with the live data off your board and the known anomaly data, to make sure that the false tests are being tested too. The false cases are being tested. And so when you're using Makefile, you're going to need to use GDB server and either ST-Link or ST-Util or OpenOCD for the debugging partnership. I use ST-Link for the flashing. My Makefile does that. And then, like I said, I use a port reader for getting I'm printing to UART, not using semi-hosting. Also, I have some other content on my GitHub that uses the old STD peripheral libraries, but those are older. And this is fresh content from, the packages you get now from ST. But I prune it. I get rid of all the HAL libraries and only use the DSP files that I'm using for the particular project. So to give you an idea, the flow is you clone this project, you build it, you build it with it's already trained, so you don't need to do the log only. You just run the inference, and it's all set for that. It's going to pull live data, voltage data, after it initializes ADC for you and pulls live data into buffers, and then it runs that buffer through the SVM model and prints the results, whether it's a 1 or a -1 for an anomaly, to the COM port. So that's your mainstream thing. And then, like I said, for extra, you can save that data from the COM port reader and save it to a file and pipe that through a trained Keras model. Again, you can clone to Windows and open it up in STM-Cube IDE, or to Linux and open it up in STM32Cube IDE. I do have some of the things zipped. But for the Makefile, it's easier to just grab the tool chains and grab OpenOCD. This is, you can, you'll have to do that on Windows through these links. If you're using Linux like Ubuntu, you can use the apt installer and so on. So I just want to make sure I'm not missing anything as far as the overview before I start diving into the step by step. I just want to mention, if you want to, I have it working on Windows and Linux, both IDE and Makefile, and I have full instructions for everything. I haven't gone through and I include a lot of the gotchas with installing ST onto Windows and so on. In the libusb library, you have to install and put it app local to ST, but that's on Windows. So I'm only going to show the Linux since it's most straightforward. So here we go. Step-by-step install for STM development environment on Ubuntu. And so what I have is I pulled a machine out of my storage. It's not being used, and fired it up, and so it's a clean machine, and we'll just walk through and install everything. I'll pause the video for the install, and we'll get the Makefile working. We'll get the flash and the run and piping it to the COM port, and saving that and piping it through the TensorFlow. So the demo will be at the end, and we'll use it all through SSH and X11 forwarding. So you don't even need to be on your Linux machine unless that's your host. I did want to show this website. I have a link to it. It's the ARM documentation on the machine learning aspects of the DSP library, and there's about 5 of them. And this is the SVM one, and you can use this as the basis for a script. You see I have a script for training one. That is checked in if you want to train your own. And if you want to learn about how it works, here it is. Okay, so here's our clean Linux machine. It does have Get installed on it. So the first thing we're going to do is install Build Essentials. The next is we're going to get all the Python environment stuff. You don't need that for the embedded, but you need that for the TensorFlow if you want to use it. Okay, you do need the USB and device libraries. And again, I'm just following along in the README on the GitHub repository at github/SteveMac321. The project name is Scikit-Machine_learning_barebones_footprint. The next is going to install the cross compilers for ARM. Next, we're going to install ST-Links tools. I use ST-Link for flashing on Linux. And then OpenOCD I use to partner with GDB server for the debugging and running. Then I use this GDB multi-arch. And then a COM port reader. I'm using this Qt.com. Now it is an X11 app, but I have X11 forwarding and MOBA Xterm, so I can run it just using SSH. Here, let's test it. Yeah, here it is, right there. And for this, I don't have a board plugged into it, but we'll want to use TTY ACM0. Anyway, we'll get ahead of ourselves here. So you have to unzip drivers.zip for this thing to build, which I just did, so I'm not going to do it again. So let's see if make works. Looks good. So it created a bin, but I don't have a board plugged in, so I better do that. It's not going to flash it, so I'll pause the video. Okay, so you just say make flash, and it does it for you. And now Qt.com reads our serial port TTY-ACM0. Okay, and so then we have a start the OpenOCD command here in the steps. And we've done it over here, and so now it's listening on port 3333. And then we'll start GDB. Okay, so we got Qt.com running, and we have OpenOCD listening in this separate port. By the way, I have a script, a Python script that merges the OpenOCD and the GDB server steps in one console running in the background. But for now, I'm showing you everything that's happening. So now we'll run GDB. So let's see, GDB multi-arch, and let's see, it's called barebones.elf, and that's it. Okay, so then we say target. You can say tar is short for it, ext3333, and we'll break in main, and we'll run. Oops, not run. I should have said continue. Sorry about that. Okay. So we're listening over here, so let's just step. I had to pause the video because wasn't printing in plain text, so I'm just going to continue here. Okay, here it is. So sorry I missed the first two rows, but they were one. The result was 1, and then the last 10 results is -1, and that's expected because I'm feeding it. The first 10 are live voltage samples right off the controller, and the second 10 are some known anomaly data that I hard code in the firmware. So it's working as predicted. So here in the code, here's the known outlier data. I just have it hard coded in here. Then here's the struct initialize with what you feed to load the model with the knowledge, so to speak. Then here's the main loop of the program. So if I have this macro defined log only, it logs the raw data that I get, and then you read it in the COM port reader, and you save that as a file, and then you feed that to the Keras model to verify or see if you get the same results, basically. Otherwise, it does the inference right on the controller. So I'm going to ahead and rebuild with this macro defined and show you what that looks like on the COM port reader, and then running it through. We'll go ahead and extract the Keras zip file and run the inference on the Keras model. Okay, so the make file creates the bin file, but to flash it, you do have to disconnect the OpenOCD. So let's see, we'll say make flash, and there it goes. I'll restart OpenOCD, so now it's listening, and we'll go ahead and run. Let's see if we got the command right there. Here we go. All right, so target T go B main continue. Where's that COM reader? There it is. Okay, so we just wrote all these floats. There's 128 floats per row. And so we've saved that to this cutecom.log. So we'll grab that. Now let's unzip the keras.zip. Okay, so let's see. Okay, now we need to set up a virtual environment for Python to run the Keras model. Okay, now let's set up our environment. Let's install pip and some Python packages. And those were NumPy, SciPy or SciPy, Pandas, and Matplotlib. And now we'll install pip install TensorFlow. And now let's activate our environment. Or let's create it actually first. And now it's activated. Oh, hang on. God, sorry about that. You need to activate the environment before you install. Duh. So I'm going to clean up, pause the video, clean up, and if actually I'll show you how to clean up if you were following along with me. Okay, first we're going to deactivate. We're going to remove it. We're going to start it again. We're creating it again, and it's starting. And now we're going to install these packages. Okay, so when you run the train, it gives you the threshold. So the anomaly threshold for this model is 0.03. And so we set that inside the train file. I'm sorry, the test file, test_live.py. And so it passes in that log file that you collected. And here's the threshold. And then here are the results. And what you can do is you can add, I have a file in there called 10 normal, 10 anomaly. What I would do is I'd take the last 10 and add it to this log file. And then, here, let's see what that does. Okay, so I ran with a file I have checked into the carrots directory called 10 normal-10 anomaly .txt. So the first 10 are the live data captured off of the controller. And the second 10 are some known anomaly signals that I got from the TensorFlow tutorial on auto-encoded anomaly detection. So there you go. And I think that's about it. I think I verified the steps. So if you go with Linux and just go through the Linux steps, I can get you here. I think I'll skip the part of the IDE. That's not a big deal. So yeah, I think that's it. We've done 23 minutes. That's long enough. So thanks for your attention, and put any comments in the YouTube or add an issue to the GitHub repository, and contribute if you like. Thanks for your attention.